This video is going to go over some example problems on how to use atomic and nuclear notation. So you will need a periodic table for this in order to kind of follow along. So make sure you have one. And we're going to look at boron-11. So you have to first find it. And remember, your periodic table starts the smallest in terms of number of atomic number. So your periodic table increases by atomic number by 1, every single one. So left to right, top to bottom, until you get to 118 there for your number of protons in the nucleus. But for this example, we are talking about boron-11. And when we find boron, we see that it's number 5. So on your periodic table, you have the B with the 5 on top, and that's the atomic number that we want, which tells us the number of protons. And all atoms are neutral, so we have 5 electrons. And then remember, to get the number of neutrons, you're going to take your mass number minus your atomic number. And the mass number in this notation is right there, that 11. So we're going to take the 11 minus the 5, and then you're going to get 6 for that one. So just remember that the bottom on nuclear notation, this is atomic number, and the top number is mass number. If I also asked you for atomic notation, that would be notation here. That would be, you'd write the element name boron-11. That would be the atomic notation for that one. For this one, sulfur 34, or S34, I just said what it was, but if we go and find it, okay, you will find sulfurs right here. And then I just want to remind you that, we're just pulling this number, the 16. Notice this 32.07, that's the average mass. It has nothing to do, we're never going to pull that number from the periodic table, okay? And then the other little value in there is electronegativity. Again, the only number you're going to pull from the periodic table, I can't emphasize this enough, is that atomic number, the number of protons, okay? So for this example with sulfur, it's number 16. So it has 16 protons, all atoms are neutral, so 16 electrons. And then we're going to take that 34, which is the mass number, that's the protons and the neutrons, and we're going to subtract out the protons. That's doing another way to think of it, because and then number of protons is 16. And so you're going to get 18 here for the number of neutrons. And then we could write it in atomic notation, which would be sulfur-34. We're going to do Ag 108, and if you find Ag on your periodic table, you can kind of see that the numbers do increase. So the higher the number, the further down it's going to be. That's silver, and silver has 47 protons, and all atoms are neutral, so 47 electrons. And then you're going to subtract the 108 from the 47, and you're going to get 61 neutrons there. I'm going to do 2 more examples here, and this is giving you the atomic notation first. And if you want to pause the video and try and solve these before I do, go for it. Otherwise, I'm just going to solve them. So if we wanted to put this in nuclear notation, it would be PB. We'd put the 207 on top, because remember, that's the mass number if you have a dash, okay? And this other one would be PB 209. So if we go and find PB on the periodic table, you're going to find it down here, number 82, and it's lead. And you might be like, oh, why is lead, PB? And fun fact for you, it comes from the Latin word plumbus or plumbic, because back in the Greek and Roman times, they had lead piping in their plumbing, which caused all sorts of health issues, but the word stuck, and so the symbol for lead is PB. But if we find this, we can see that lead is 82 protons, so, and then all atoms of lead are neutral, so 82 electrons. And then if we take this 207 minus the 82, you're going to get 125 neutrons in this one. And in lead 209, still 82 protons, 82 electrons, but you're taking 209 minus the 125, or sorry, minus the 82, and you're going to get 127. And so, look, these are both atoms of lead, and this is why I want to emphasize that any one atom can have different numbers of neutrons. So if we look at my question here, the bottom is, what is the term for two atoms that are the same element, but they have a different number of neutrons, meaning they have a different mass number, because this can happen, okay? And if you kind of saw when I flipped earlier, you'd see that it's an isotope. This is a key understanding. So the number of protons doesn't change, because if you change the number of protons, then you've changed the element, but any one atom of lead or even hydrogen can have different number of neutrons. So let's kind of find out more. Why is this? So they are atoms that have the same number of protons, but they have different number of neutrons. So they're the same element atomically. You wouldn't be able to tell them apart, but they vary in mass numbers because of different number of neutrons. They do typically have very similar physical properties, meaning if you had a hunk of lead, you wouldn't be able to be like, oh, this part of it is lead 207 and this part is lead 209, okay? But some isotopes are radioactive. So like uranium is a common one. You can go and buy some isotopes of uranium on the internet, and you wouldn't be considered on the watch list because they're not radioactive. But some isotopes of uranium are radioactive, and those are the ones that are used in power plants, nuclear power plants, and in nuclear bombs. So know that certain, like a hydrogen has isotopes where it has a neutron in it, and it's called deuterium, and then it has another isotope, which is radioactive, that has 2 neutrons in it. Not very common, but that's where you get the average atomic mass from. So why do they exist? They exist because the nucleus wants stability to spread out those protons, but the difference here is that there can be different number of neutrons that can be effective for making that separation. So just remember, like charges repel, too much positive charge all in that small nucleus would be unstable without the neutrons. However, there isn't like a set number of neutrons for any one element of how that can be. And so a great image here that kind of shows you this is this one. So if you imagine an atom with 3 protons, you should find, 3 protons on your periodic table is lithium. So we're looking at lithium here. And if you just had 3 protons, this example here, that would not exist because you'd have too much positive. And you can see that that would not be stable. However, these next 2 pictures of lithium are actual isotopes of lithium. They actually do exist. So if you want to label, this is a neutron, this is a neutron, this is a neutron. And so this atom of lithium here is going to be, it would have mass number 6, okay? Because 1, 2, 3, 4, 5, 6, there's 6 subatomic particles in the nucleus. So this atom of lithium would be mass number 6. It'd be 3 there if you were going to do the nuclear notation for it. Versus this one here has 4 neutrons to spread out that positive charge. This would be lithium 7, okay? And now let me tell you that both of these isotopes of lithium both do exist, okay? So now I'm going to actually tell you to look at a number that I told you not to look at. And if you look at the average atomic mass, so let me go back to this, of lithium here, you see this average atomic mass is 6.94. So what does that 6.94 tell us? That tells us, okay, 6.94 is the average atomic mass. So the periodic table does a lot of things. And what it's telling you is that of all the lithium atoms in the whole universe, that about 94 of them are lithium 7. Okay, this is the more common isotope, and about 6 of them are lithium 6, and the average of that is 6.94. So that's where why you can't look at the periodic table and get the mass of any one atom of lithium or anything, but you can get the average. Because if you were to have a hunk of lithium or a hunk of any other element on the periodic table, it would have an average mass because the ratio of however many isotopes there would be of any one atom is pretty much set for that. So another example here, mass number and atomic symbols for the following 3 isotopes. If you were to look at this picture, I'm going to go fast, but if you want to pause it and kind of look at it a little bit closer, here you would see that there are 6 protons and 6 neutrons here, and so this is carbon 12. And if you were to look at this one, you'd see that there are still 6 protons, but there are 7 neutrons. This is carbon 13. And this one, there's 6 protons and 8 neutrons, and this is carbon 14. And if we look at our periodic table, okay, the average atomic mass of carbon is 12.01 is the average. So what that says is that 99.99 carbon atoms in the universe are this one, because it's really close to 12, and that 1 out of 100 is either carbon 13 or carbon 14. But if you have a hunk of carbon, which if you're writing with a pencil right now, that pencil lead is actually carbon graphite, most of that is carbon 12, okay? And so the average atomic mass tells us what isotope is most common or most abundant because it's taking an average of those samples. So that ends this presentation, and you should be able to solve for atomic and nuclear notation problems with this, as well as understand isotopes and why we don't use that average atomic mass.